Good morning, everyone. I'm going to talk about how I used machine learning to improve the quality of the UK Renewable Energy Planning Database, known as RAPD, and why this matters for the bank. The core problem here is about missing and inconsistent data. Relationship managers in the bank, they rely on RAPD data to understand new solar, wind and battery projects. But many records are incomplete, especially one of the most important fields, installed capacity, which tell us the size of a project. Because of these gaps, I cannot compare projects fairly. Analysts spend a lot of time manually cleaning files, and some lending opportunities remain hidden simply because the data is not filled in. So the business question was, can I use data I already have to intelligently predict the missing fields and give relationship managers clearer insights faster? My goal was to build a process that is reliable, understandable, and directly linked to better lending decisions. So how I approached it? I followed an industry framework called CRISP-DM. Think of it as a recipe with clear stages, like understanding the business need, understand the data, prepare it, build models, evaluate, and deploy into real tools. This structure ensured that I was solving a real operational pain point, not just an academic exercise. For the work, I used Python to process and model the data. I chose Python for its robust libraries for data processing, modeling, and visualization. I also chose Tableau and Excel to explore patterns and CSV files as inputs to the pipeline. For modeling, I used K-means clustering to group projects into technology-driven segments, then built the linear regression model within each segment, followed by random forest and XGBoost. So I used random forest across the full data set and within each cluster as it handles nonlinear patterns, and XGBoost was included as an extra benchmark for performance comparison. So the tools and the approaches that I chose will provide relationship managers with clearer and more consistent project insights, and will also support the climate data team with our data completeness and reliability as well. Understanding the data. So when I explored the data set, I immediately saw that it is really a mix of different technologies. A solar farm behaves nothing like a wind farm. Solar capacity is strongly linked to site area, bigger land, more panels, more power. Wind capacity depends on turbine height and total capacity, and number of turbines as well. It's like comparing apples and oranges. If I try one single formula for everything, the answer will be blurred. Continuing with my analysis, the correlation matrix reveals the strongest correlations between installed capacity and solar site area, and installed capacity and number of turbines, with correlation coefficients of 93% and 80% respectively. We also have the blocks plot here of installed capacity for solar and wind, showing that most values are clustered at the lower end, with a long tail extending toward higher values, confirming the presence of outliers. Building on the distribution analysis from the blocks plots, the pair plots provide further insights. Most solar projects are in England. Larger wind projects are concentrated in Scotland. Outliers often reflect genuine mega projects, so I kept them, which confirms that applying K-means clustering and using linear regression on the clusters can capture real operational differences between the technologies. Data preparation steps. I first cleaned the data and encoded categorical features for consistency. To choose the number of clusters for K-means, I used the elbow method. The chart showed the elbow around 3 or 4. And for the checks in code, confirmed that K equals 3 was optimal. So this preparation ensured consistent inputs for clustering and regression, helping me make more reliable capacity predictions. After clustering, I applied linear regression within each cluster. Cluster 0 performed very well with a root mean squared error of 9.7, showing that the predictions were close to the actual values, and a mean absolute error of 3.5, meaning the average difference between predicted and actual values was small. Cluster 1 performed poorly because the data was highly variable, and while Cluster 2 had moderate performance. This shows that segmentation works best when the clusters are internally similar, but is less effective when the data in a cluster is diverse. So for benchmarking, I tested three main approaches. The linear regression. This is the classic transparent model. It assumes the world is a straight line. If A increases, B increases proportionally. This is great for explaining relationships to relationship managers. Random forest, think of it as a committee of decision trees instead of one line. Each tree gives a vote, and together they capture nonlinear real-world behavior. This method is known for stability, handling outliers, and not being fooled by complex interactions. XGBoost, a more advanced boosting technique that learns step by step. However, with my relatively simple features, it underperformed. The top three charts show predicted versus actual values across the full dataset. Linear regression and random forest had an R-square of 86, which means it was able to explain about 86% of the variation in the data. In other words, its predictions were very close to the actual values. XGBoost, on the other hand, had a lower R-square and higher errors, meaning its predictions were less accurate and further from the actual values. The figure below compares performance across clusters. For cluster 0, linear regression performed similarly to a random forest with comparable root mean square error and mean absolute error, meaning the predictions were about as close to the actual values as the random forest. In cluster 1, both the random forest and XGBoost performed better than linear regression. For cluster 2, linear regression outperformed the other methods, showing higher accuracy and a smaller prediction error. A likely reason XGBoost didn't perform as well is that some clusters have small or highly variable data, and the relationships appear mostly linear, which simpler models like linear regressions can capture more effectively. So the analysis shows that cluster-specific regression works best when projects in a cluster are similar, because it can capture the specific patterns of each technology. Performance drops in clusters where projects are very diverse, a natural limitation of segmentation. Looking at global models across the full dataset, random forest delivers more stable and reliable predictions. XGBoost didn't perform as well because the data features are relatively simple, while random forest can handle nonlinear relationship and reduce overfitting, making it more robust. The key takeaway is that a hybrid approach would be most effective. Cluster-specific models help identify technology-level differences, while a strong global model ensures consistent predictions for all projects. From a business perspective, this improves the accuracy and completeness of RAPD data, helping climate DNA team and relationship managers make earlier and more informed decisions with reliable insights. Deployment. The predictive model is designed to support the climate data team and relationship managers, giving more complete project information and reducing manual follow-up. To make implementation easier, I created an ETL, extract, transform, load, a workflow to operationalize the model. This workflow handles extracting the data, transforming and cleaning it. enriching it with additional attributes, and loading it into the system. So it's ready for analysis and dashboard. Figure 12 illustrates this process, showing how these steps ensure the model can be applied efficiently and consistently. By using the ETL approach, the model can be deployed smoothly, maintained over time, and provide reliable, up-to-date insights to support decision making. Impact and conclusion. So I completed an exercise where I used linear regression on cluster 0 to calculate the impact of predicting missing installed capacity values for solar projects only. So this analysis identified approximately 237 million in potential lending opportunity that is currently being missed by the relationship managers. So this just goes to show how the model can improve the visibility of projects with incomplete data. In addition, filling in these missing values reduces the manual effort needed to work with incomplete RAPD entries and increases the reliability of downstream analytics as well. So with this more complete data, relationship managers can engage with customers earlier, compare projects across different technologies, and prioritize opportunities more effectively as well. Cluster-specific models are particularly useful for identifying patterns within similar projects. In Cluster 0, linear regression performed well. For project groups that are more diverse, random forest provides more consistent and accurate predictions, so that could be implemented in the future. So a hybrid approach combining cluster-specific models for homogeneous clusters with random forests for heterogeneous groups ensures accurate results across all project types. We also have here figure 13 that illustrates the potential lending impact if we apply the linear regression to cluster 0. So it shows the potential lending, the current potential lending for wind onshore and solar. And the following chart shows the potential lending with the prediction, showing a potential increase of £237 million in potential lending. In terms of next steps, we could include validating the model outputs with subject matter experts, implement automated data quality checks, scheduling periodic retraining, and integrating the results into dashboards and reporting systems. So these steps ensure the model can be used regularly and consistently, providing reliable information for decision making. So in conclusion, this exercise demonstrates how predictive modeling can be applied effectively to renewable energy project data. The hybrid approach provides a reliable framework for ongoing analysis, and the methods developed can continue to support decision making and planning as more data becomes available.